Hi, my name is Arseni. I'm a PhD student in Ben-Gurion University in Israel, and this is a joint work with Ronny Stern, Ariel Fellner, and Roy Zivan, enhanced multi-agent pathfinding by using artificial potential fields. First, let's briefly introduce the problem that we're working on. Multi-agent pathfinding, that is a graph of vertices and edges, and we have some predefined amount of agents, we have a start locations, goal locations, paths, that is a set of vertices from start to goal. An objective is to minimize the sum of all paths of agents. An important variant of MAPF problem is so-called lifelong MAPF, where new targets are generated upon agents arriving to existing targets. In LMAPF, we want to maximize the throughput, that is the number of visited targets by all agents. So let's start with the motivation for the work, and that emerged from the following observations. When we implemented many popular MAPF solvers, we paid attention that a lot of the following phenomena. In many scenarios, agents create a highly packed congestions somewhere in the graph, and that is, in turn, made the search more difficult. So maybe it's better to surround agents with some artificial potential fields, and the movement will become hopefully smoother. The agent will preserve a distance from each other, and the solvers will find paths quicker. So let's define a simple formula for the APFs. So for an agent I, we define for every vertex V, and VI in formula refers to the current location of agents, the following formula. To define APFs, we need three basic parameters. W defines how strong the field, gamma defines the rate of decay, and Dmax defines how far APFs will propagate. Given all these three parameters, we can provide a specific number that represents APFs for every vertex. So these are the repulsion forces of the agent. And in the paper, we'll also show exactly how we define the attraction forces for the targets. So first, we implemented the simplest possible naive adaptation of the idea. We implemented the attraction forces on the targets and the repulsion forces of the agents, and no search is executed. In this form, we let agents to flow the magnetic fields and those artificial potential fields. And here we very quickly discovered that the agents, in many cases, are trapped in deadlocks and life locks, as like here in the narrow corridor in the example. Then our next idea is to somehow incorporate those APFs inside already existing single-agent pathfinding algorithms. But before that, we want to adapt the formula for single-agent pathfinding algorithms, and we need to introduce the time dimension. So here the formula is basically the same, except that we also define APFs not only for every vertex, but for every given time step. And the pi it is the agent locations at the given time step. So here as well, we need three of those parameters: W for the strength of the field, gamma for the rate of decay, and Dmax for the distance of propagation. So let's try to incorporate APFs into A-star search, a very popular single-agent pathfinding algorithm. A quick reminder of the building blocks of the A-star search. We have, for every agent, we have a G value. We have an H value. G value composes the cost of the parent node plus the cost of the moving to the current node. And H value is approximate cost for the future node. And F is the sum of two. And the sum of two. And G, as we said, is the cost of the parent node plus some cost of going to the current node. Mostly it's one. Okay, so we need to append somehow additional costs of APFs to the A-star node. The big question is to which part to add APFs, to G or to H? So when first making our preview, many reviewers were convinced, and they also tried to convince us, that the obvious way is to add those APFs costs to the H part, so that the H agent will be defined as follows: some distance estimation plus APFs. So in the paper, we show exactly why this will not work. And basically, the agents will simply act as if there are no APFs at all if we add the APFs cost to the H part. and they will pick, for example, here, the red path that is undesirable. Goes exactly through the APFs of other agents and want the black path to be chosen. So we show here that if we compose the G node with the APF costs, the G part of the node with the APF's costs, here we get the desired result when the path is chosen is the red path. In the paper, we also show how to incorporate APFs into ZIPs, PIBT, and LACAM algorithms. So in the experiments, we compare different approaches of LNS plus A star LNS with the ZIPs, PRPs, this stands for prioritized planning with the A star, PRP with ZIPs, PIBT, and LACAM star. And we see that, and here are the results. The dashed lines are the APF enhanced versions of these algorithms, and the solid lines are the basic versions of these algorithms. You clearly see that when we look at the y-axis, which stands for throughput, we see that the APF enhanced versions succeed much higher throughput, and this is good, than their basic non-APFs versions of the algorithms. Here, the parameter sensitivity analysis, and we checked every parameter and we found the best parameter that works for all the maps. Once again, all the details in the paper. So that's it. APF works. APFs improves throughput in LMAPF significantly. APFs are easily adaptable to the existing algorithms, and this is great. And yeah, thank you.